Welcome back, everybody. I handed back all of our exams. My request to you is, so I am human. It should be no surprise that every once in a while I do make mistakes. So what you'll see whenever I grade something is I put the score on it, and at the very bottom right of any page, there should be usually, unless it's just one question on the problem on the page, there should be a number there. Please make sure that on every page that number is adding up correctly. So like if you got 5 points to the first one and 5 points to the second one, you should get 10 points in the bottom right. It should say a 10 on the bottom right. If that's not the case, let me know. We can fix it. If it as long as it's higher, as long as it's supposed to be higher. Don't tell me if I accidentally added and gave you more points. Because otherwise then I have to take it away. And then the other thing is make sure that that number, as long as it's correct, that it's been transferred to the front correctly. And if it isn't, let me know and we can fix that. And then finally, make sure that the numbers added in that front page, make sure those add up to the number that's given. I usually don't make a mistake. I usually double check every single one that I plug in. But that being said, I can make mistakes. I remember my first semester teaching, I accidentally put in a 5 instead of a 15. So a student dropped down a whole letter grade because I had made a calculator error. So my finger didn't register the 1. So that's what happened. As a reminder, so it is official now. You have until next Wednesday, the beginning of class, to turn it in for as a redo. Now, I would really, really appreciate it if the way you did it is, let me get I'm going to use this student's exam as an example. So this is the page. This is page 3, right, on your exam. What I'd like you to do is, if you got anything wrong, if you want to correct anything on this page, go to the other side. So this is do the corrections on this page. Like on the back of the page previous. That way I can look at both of them at the same time. It's not wrong to do it the other way, but it will make me mad because then I have to run around and keep checking. Like this way I can look at the original work, because and the reason why that's important is that the grade on the redo, it depends upon what grade you got on each page. So when I'm grading this, I'm looking at each one and making sure to give you the proper amount of points. So it really helps me out if you put your corrections on the previous back page. You do not need to redo the entire assignment. Only the problems that you want to have regraded. So if you got full points on a page, you don't need to redo that page. It's only the things that you want to have regraded for something. Let's see here. What else? As a reminder about it, the implication here is that there is no outside help besides me. So you can absolutely come to my office hours. You can send me emails, anything like that. Ideally, if you want the fastest response, try and tell me if you're stumped on the problem, tell me what you've tried. If you're truly, truly stumped, I can give you a hint. I'm happy to do that. Ideally, take pictures of the question that you're struggling with. That way I can see what you went, where you went right and where you went wrong. I don't have them all memorized, what you guys did, right? I don't have all your exams memorized. So take a picture of it with your phone or scan it or whatever. Doesn't matter to me, but send that in an email if you want to have an email correspondence. It makes it so much quicker than other than me having to go I'm having trouble with question 5. Let me say, what have you tried in question 5? Well, I've tried this. Can you send me a picture so I can see it better? Because it's hard to explain mathematics in text. So that's the type of thing. Please send me a picture. It makes so much faster response rate. But you can absolutely also meet with me during my office hours, which once again, in case you do not know, my office hours, and you don't need to write this down. It's on our website. You can always find a link to my office hours, which you can attend both in person in my office, which is right across the way in Building A, or you can attend virtually via Zoom. You just need to have Zoom installed on the device you're looking at it with. But my office hours are 9 a.m. to 12 p.m. on Tuesdays and Thursdays. So please feel free to join those. I'm happy to meet with you and help you out to understand this process. As a reminder, the whole goal of the redo, it's not so you can get points back. I mean, that's a byproduct of the whole thing, but the main thing is to learn from the mistakes that you made. So sometimes it's great to figure out those mistakes by yourself, right? But other times it's hard to figure out what went wrong. And I'm happy to help you with that. That is what my main goal here is. So you can absolutely come to me for questions. You cannot go to anybody else. This includes the tutoring center or any tutor that you have. So no outside help besides me. Nothing, like no human component, no solving component. So no Mathway, no Wolfram Alpha, anything like that. If I do find that, if I even suspect it, I will give you a 0. And I will have to and by virtue of that, I will have to go through with the academic misconduct. So please do not use those things. There's plenty of time to email me and ask me questions. That's why there's a week to do this. So, yes. Like with a tutor?
No.
Yeah, that's fine. Looking at checking a problem in like Wolfram Alpha to see if you got the right answer after doing it. Is that what you kind of?
No, I meant like if you had a similar problem with like.
Excellent question. So absolutely. You can I should clarify. So no solving apps, no outside help. However, any non-human or solving resource, whether that be online or in or in a book or a textbook or notes or anything like that, any of that can be used to figure out your mistake. So you can absolutely bust out, go to the library, buy rent out every calculus textbook. You can do that. Look online, go to Paul's online notes, there's a link in my on our homepage for that. Any of those things, totally fine to do. It's just, I want this to be coming organically from you. I want this to be you looking at the problems and figuring out where you went wrong and learning how to do the problem yourself. With guidance from your teacher as well, if you need it. Additionally, by the way, so those are my scheduled office hours, but I'm happy to meet with you guys one-on-one at a different date if those times do not work with you. My main, yes.
Oh, I was gonna ask what days are your, I know there are Tuesdays and Thursdays, but what time is your office hours?
9 to 12. And then in building A, room 160D. Building A, room 160D. So building A, room 160D. I have a bunch of cool stuff in my office. I got an Euler disc. I got Pokemon plushies and stuff like that. Not that I've ever played, but it's a fun room. So please stop by. But if you can't make those times, I'm willing to try and work with you. Just send me several times that work in your schedule. That way we don't have to play phone tag. Because it's like, hey, can you meet me at 12 o'clock on Friday? No, I can't meet you. Can you meet me at 1 o'clock on Monday? No, I can't do that. I don't want to do that back and forth and back and forth. So because it'll take longer and just be frustrating for especially for you, because you really want to get this done. So just send me several times that work in your schedule. And I even if they're later in the day, like you can say, hey, Phil, can you meet at 7 o'clock? I've even met with a student at 11 o'clock at night at one point. That was before Phoenix was born. So that's not really that much of an option anymore. But like 7, 8, 9, I can do that. But I'm happy to do that. Just let me know. Yes, Derek. Anybody can like during my scheduled office hours, anybody can show up during my those ones. And if you're in the same room, like, so let's say 3 people come to my office hours during that time period, asking for questions on the exam. That is a situation where I am monitoring the whole situation, so you can be in the same room with another classmate working on your exam redo. So don't feel like, oh shoot, there's a person in there, I can't go. That's totally fine because I'm there to facilitate it. So I can stop anybody from, like, I know none of you guys would do this, but like just one of you guys running in down the hallway in my office saying the answer to 5 is 16. That'd be really weird. But just it's fine for multiple people to be in my office hours at the same time. Additionally, if you think that anything was graded unfairly, or you think you deserve more points, please advocate for yourself. I'm more than happy to hear you out. I will never make you feel bad for advocating for yourself in this situation. It's important. And it could be that I made a mistake. Every once in a while, I trying to grade something and I get distracted or something like that, and then I don't give the proper points. It doesn't happen very often, but it can happen. Other thing is, if you're wondering how many points you can get back, there's like basically all you need to do, like new score, new potential score equals original score, the OG score, plus 100 minus the OG score divided by 2. That's how you can figure it out. So if you get an 80, you put in 80 plus 100. I'm going to write it down just so we don't have a million things in our mind at the same time. So if you got an 80, that'd be 80 plus 100 minus 80 divided by 2, which should end up being 90. So if you get an 80%, you can get a 90. You can get an A minus. If you get a 50%, you can get a 75. You can go from a C to go from an F to a C. So it gets like, yes.
So like technically, could we just do the problems to make up for however many points, or should we try and fix everything?
I would encourage to like any problems that got marked down partially, that would be, I would do them personally. But that I know that is a tall order because you guys, I know that this is not the only class that you guys are taking. So I don't like, it's not a problem if you don't finish a few of them. Just know that if it's not on there, I will not grade it. Like if I don't see it, I won't grade it for points back. But it is not like, I know there's certain problems where you only like some people only miss like a half of a point. And like, do you really want to go through all the work just to get a 0.25 points back? I get that. You don't have to, but it is fair to do so. What was I saying? All right. Any questions on that? Nothing?
I'll explain my calculator
It might be that you what I'm thinking happened. If you have that calculator, you need to put your entire numerator in parentheses. Otherwise, it'll only just take your original. It'll add 100 and then divide your original score by 2 and subtract that. So that won't work. So put your thing in parentheses and then divide by 2. Yeah. So you have until Wednesday of next week. So I'll have office hours tomorrow. I'll have office hours on Tuesday. And then if you do need help at additional time periods, just let me know and I'll do my best to meet with you. Okay. And so a couple things also on that one. I said it before, but I will mention it again. We're really pleased with the performance just on that one question about is it continuous, because almost everybody got that right with a mathematical justification, which I haven't seen in the 10 years that I've been teaching. So kudos to you guys. That was awesome. The last 3 problems seem to be hard for a lot of students. So I was a little bit bummed because I kind of hinted at the fact that there was going to be a definition of the derivative problem. So I was hoping not to see any of those blank, but it happens. Once again, I don't presume to know that this is the only thing going on in your life. So, but if you need any help, please feel free to ask. You guys actually did better than this isn't the exact same exam. I've modified it a little bit, but You guys on average did better than like last two math classes last two calc classes that I've taught. So kudos to you guys. Okay. Anything else? Okay. So we'll go ahead and get back into implicit differentiation. So just to kind of recap what we did last time, there's this whole process. You differentiate both sides of the equation where we're thinking of y as a function of x. And so remember, you put the ddx at the very beginning of each expression on the in the equals in the equation, not the ddx at the end. I will mark you down a point for doing that because that is not mathematically valid. That is trying to take the derivative of nothing. Whereas if you write this, you're saying take the derivative of y cubed plus y squared minus x squared, and then also take the derivative of 5y equals 4. Then, and we'll re-hit it. So once again, the reason why y cubed's derivative was 3y squared dy dx was up above is the fact that y is being treated as a function of x. So when you're looking at this, you really got y of x to the third power. So the outer power, like the outer function is the third power. So you're going to do a chain rule, 3 to the second, 3. And then the second power of y of x times the derivative of y of x, but y, like the derivative of y of x would be y prime. So that's why it's 3y squared dy dx. In practice, basically, take the derivative like you were taking the derivative with x and then tack on a dy dx. In practice, that is what's happening, but I would much rather you understand the reason why it's happening. So you differentiate the entire equation, then you isolate the dy dx terms from the non-dy dx terms. In this situation, there's only one non-dy dx term. So convention is to bring the dy dx's to the left. However, I like to try and make all my terms positive wherever possible. So if it ended up being that these were negative here, if this was a minus sign and this was a minus sign, I would probably bring things to the right just because I like making my numbers positive. That being said, it is not wrong to do it one way or the other, just as long as you're consistent. I guarantee you. So if you're looking at the exercises in the back of the book or like in the back of the section, or you're looking at things online, you might get a different answer, but your answer will probably be just off by 2 minus signs and a numerator and denominator, which will make things just fall out naturally. So if you're ever uncertain whether you got the same answer or not, just plug in a value for x and a value for y and see what you get on both equations, and you should be able to find out. Now that you've got all the dy dx's on one side, you factor it out and divide to get the dy dx by itself, and that's your derivative. And as we said before, yes, your derivative now has x's and y's, which makes sense because your original equation was in terms of x's and y's. There was no way to write it purely in terms of x. So that's what we get. Any questions? Yes, Chase.
Sorry, I think I missed this part when you were explaining, but I don't understand why the negative 2x is not also being times by derivative.
So, great question. So why is this term right here, doesn't have it a dy dx? Because, and this is why it's important to look at the terminology here. This is the derivative, this is ddx, the derivative of this equation with respect to x. So when I'm taking the derivative of x squared, I'm taking, like, it's a normal derivative. So it would be 2x, like it would just be 2x. There's like, technically speaking, ddx of x squared. And this is once again why Leibniz's notation is so useful and why this made the rest of Europe advance so much faster. Technically speaking, this would be 2x times dx dx. But then the dx's quote unquote would cancel, and that would just be 1. So that's why it's 2x. So, and once again, if there's a secret mathematician out there that's just trying to catch me off guard, dx is not a fraction. So you can't technically cancel it. However, if you can think of it, like you can occasionally think of it that way, and so it would be the derivative of x with respect to x, and that would just be 1. So dx dx would cancel itself out. That's a reason why in stark contrast, the y squared, you're taking the derivative of y with respect to x. So y is a function of x. Does that make sense?
Yeah.
So it's the same. Let's see here. Let's look at another example. I want to restart and try and think of a different way to explain it for a moment. Because we are taking the derivative with respect to x, like we normally do, y is considered as a function of x. It's the same reason. No, that's not gonna be a good way to describe it, but it has to do with purely the fact that you're taking the derivative with respect to x. If I wanted to do d dy, so this might be useful to see on a side. So if I did this instead, if I did d dy of y cubed plus y squared minus x squared, if I did that, if I took the derivative of the left hand with respect to y being the variable, this would be 3y squared plus 2y minus 2x dx dy. So it depends on what variable I'm taking the derivative with respect to. So here, I'd be taking the derivative of y cubed with respect to y, and that would just be 3y squared. And here we'd be, like in this case, we'd be implicitly thinking of x as a function of y, hence why I get dx dy, which looks weird, absolutely, but that's the stark difference. Does that help better explain it? Yes, good point.
So like, if we do the product rule and you know how we find the derivative of x and then g of x, when we do the g of x and say that it has y, and then we would have to fit dy over dx, but in the f of x, it would just be normal.
Ah, it's a good question. And so the answer, like, if I understood your question correctly, then the answer is yes. And we're going to see an example of that in just a second. So, any other questions before we move on to an example? All right. So, now that we know how to do this, instead of having to solve for like the original example, where it was trying to find the tangent line to x squared plus y squared equals 25 at 3, -4, where we had to solve for y, determine which function to use, the positive square root or the negative square root, then take that derivative and everything like that. We can do it now. And so what we'd have to do is, if we're going to find the equation of the tangent line, we need the slope. And the way to do that would be to take the derivative of both sides. So ddx of the left equals ddx of the right. And this is where I really recommend color, to show you that I am now taking the derivative of the equation. So I'm going to put x squared plus y squared on the left, and the derivative of 25 on the right. Yes. ddx and so ddx, excellent question. What is the Charlize is asking, what is the difference between ddx and dy dx? So dy dx is a derivative. It's the derivative of y with respect to x. ddx is an operation on something to take the derivative. So if I write dy dx, I'm saying that's a derivative. Whereas if I say ddx, I'm saying take the derivative of what I write. So as a stark contrast, if I was to write square root versus square root of y, right? The right-hand side is the square root of y, whereas ddx is taking the square root. So ddx is an operation on an expression. Does that make sense?
Yeah.
So when I write ddx, I'm saying take the derivative of whatever I've written. dy dx is an actual function. It's a derivative, that is.
Function of a derivative.
Well, the derivative is a function. So it's the derivative, yeah. So now that we've applied ddx to both sides, and it does need to be ddx, dy dx would be multiplying by the derivative, which is not what we're trying to do. We're trying to take the derivative of both sides, just like you would try to take the square root of both sides, or you try to add the same number to both sides, or divide both sides of the equation by the same number. We're taking the derivative of both sides. So the derivative of x squared with respect to x would be 2x. the derivative of y squared with respect to x. Keep in mind that terminology, very, very important. The derivative of y squared with respect to x would be 2y dy dx. And as we said before, you can write y prime, but I always recommend not doing that because then it starts to look like y to the first power, and I don't want you guys to get tripped up by that. If you do want to use y primes, what I would recommend is using a different color or maybe writing it bigger.
Yeah, right, dy over dx, that's the derivative of that.
Yes, that is going to be the derivative once we isolate it by itself.
Why not just call it y prime equals that?
Well, because we haven't solved for y prime yet. We haven't solved for dy dx. We have to actually take the derivative of everything and isolate the dy dx's. As we saw in this previous example, there were multiple dy dx's, and we need to get them all together.
So we're claiming that's the derivative.
That will be the derivative once we solve for it. And then the derivative of 25 with respect to x, 25 is a constant, so it's going to equal 0. So we want to, now that we've taken the derivative of both sides of the equation, we want to isolate the dy dx terms from the non-dy dx terms. So minus 2x, exactly right. We get 2y dy dx is equal to negative 2x. So that means the dy dx is equal to negative x over y. A pretty nice derivative, actually. And this actually brings up a very, very interesting thing. So one of the things I do love about implicit differentiation is if the equation is somewhat pretty or symmetric, it almost always ends up being that your derivative ends up being pretty and symmetric. You'll see what I mean in a little bit. But x squared plus y squared equals 25. That's kind of like nice and pretty. X squared, y squared. And now the derivative is just negative x over y. Very pretty. Yes.
I was thinking of just minus 2x minus 2y on both sides.
But the 2y is applied, is being multiplied into that dy dx. So we've got to divide to get rid of it. So that's the derivative for any values of x or y, but we want the equation of the tangent line at 3, negative 4. So to find m tan, we evaluate dy dx at 3, negative 4. So just remember this notation, we write a vertical line. This is a common notation in mathematics. If you write a vertical line and then write something at the bottom, that means that you're taking whatever equation you have or whatever function you have, and you're evaluating it at those values. In this case, when x is 3 and y is equal to negative 4. So this would be negative 3 divided by negative 4, or just 3/4. And that is our m tan. So negative 3, that's a negative 4 right there. I plugged in negative 4. It just looks terrible. You guys can't tell that that's a negative 4. That's clearly. No, I'm kidding. I'm wasting time. I'm being stupid.
Where did the negative?
The negative sign was from here. Now, yes, this is taking longer right now, but you'll see later on, especially with ones where we wouldn't be able to solve for x in a nice way, where this is much more efficient. So that's the slope. And then the point was already given. The point was already given, 3, negative 4. So bringing these two things together, we get y minus negative 4. So y plus 4 is equal to 3/4 x minus 3. And I'm just going to leave it like that in the interest of time, but you could write it in slope intercept form if you so preferred. All right. This next one, unless there's any questions on this, and thank you guys are asking excellent questions on this stuff. This thing is not intuitive by any means. Yes.
Did you write that as y equals this?
Sure. It would be y equals 3/4 x minus 9/4 minus 16/4, so minus 25/4, like that. Plug in 0. Let's plug in I think that should be right. Not negative 9/4 minus 4, which is 60. Yeah. So the next one. So this gets to Capri's question about what to do with all the rules. So we're going to see that here. The derivative, find dy dx in the following equations. So 4e to the 3x plus natural log of y equals y to the 5th. First thing to do is take the derivative of both sides with respect to x. So ddx of the left equals ddx of the right. I always just like as a time-saving technique, I write like since I'm going to be using a different color anyways, I just write out, give myself a large enough space. It's okay if it's too big, right? It's okay. If you just have to like space it out a little bit, maybe give yourself too much space, it's fine. But ddx of both sides of the equation. So 4e to the 3x plus natural log of y and derivative of y to the 5th. The first term is purely in terms of x. So it's going to be taking derivative like normal. E to the 3x, that's a chain rule. It's a quick chain rule, but it is a chain rule because the outer function is e, the inner function is 3 to the x. So what we end up with is 4e to the 3x times 3. And then the natural log of y, you're going to take the derivative of that. That's natural log of y of x, because y is being thought of as a function of x. So it becomes 1 over y times, and I'm probably just going to do this, ddx of y, like this, times the derivative of y. Or dy dx, however you want to write it. And then equals, that's dy dx, equals 5y to the 4th times dy dx. I normally would just write dy dx instead for like the purple thing that I wrote. I would normally just write that, but since it's a new function, we've only been dealing so far with just powers of y, but I wanted to show you what's going on here. So the derivative of the outer function is natural log, the inner function is y. So the derivative of natural log is 1 over x. So in this case, 1 over the inside function, so 1 over y, times the derivative of the inside. The derivative of y would be y prime or dy dx. And looking at this, it doesn't matter which one I decide to do. If I decide to bring them to the left or to the right, I would meant like if I bring my 1 over y dy dx to the right hand side, I only have to do one piece of algebra. So that's what I'm going to do. This gives me 12e to the 3x equals 5y to the 4th plus 1 over y parentheses dy dx, not plus, minus. And I skipped a step here, so please ask me if you need me to show that step. Sure. So you get 5y, the 4th dy dx, minus 1 over y dy dx. And then you can factor out a common factor of dy dx. 12e to the 3x equals, parenthesis, 5y to the 4th minus 1 over y dy dx. And that gives us, at the end of the day, dy dx is equal to 12e to the 3x divided by 5y to the 4th minus 1 over y. And that is our derivative. In the interest of time, I'm going to give you guys the answer to B. I'd like you guys to do it on your own time, but the answer should be, okay, dy dx is equal to 49x to the 6th divided by 5 halves y to the 3/2 plus 2 cosine of 2y plus 3. Let me just make sure that's right. Yep, that's right. Yes.
So like sine we can differentiate with respect to x and hence taking it just cosine 2y plus 3, and then when we go inside, we have to do dy dx for 2y.
Yes.
Okay.
So when you're taking the derivative of the sine of 2y minus 3, or 2y plus 3, the outer function is that sine. So you take that derivative, that's cosine, times the derivative of the inside. The inside here has a y in it. So when you take that derivative, you get that 2y dy, 2 dy dx. That's why we get that. Good questions. So that's the answer to that one, just to save on time. And once again, if you're concerned with how I did that so quickly, once again, I've been doing this for a long time. Done this for a very, very, very long time. So I know the tips and the tricks, and I can do it very quickly in my head because I've been doing it. I don't expect that from you guys. This is something that you're still learning. It might take you a little bit of time. There's a usual convention that I remember from when I was a grad student, like when I was asking one of my my mentors, like, how do you decide, like, how long did, like, how many questions to put in an exam? And he said, like, I usually take whatever time it takes me to do a problem and multiply that by 5. Just to allow for this chance of understanding the problem, whereas I know exactly what to do. So you will get there. You will get there. And then this will become a superpower for you. And then you can impress all the people you know. Okay, this one right here. This gets to Capri's question exactly. So we have x squared y plus xy squared equals 2. Notice the symmetry, right? X squared y plus y squared x, right? There's 2 terms, each one that just they flip this the power on both of them. So we will solve this by we will find the derivative by differentiating both sides. So d dx of the left-hand side equals d dx of the right-hand side. So x squared y plus xy squared -2. Now, when you hashtag get good, when you hashtag get good with this stuff, you don't need to do it. But I would recommend when you're starting out, maybe just doing some side work to figure out the derivative of each one of those things separately. So d dx of x squared y. The derivative of that with respect to x. This is a product rule. You have a product of an x function, x squared, and the product of another x function, y of x. So it's a multiplication, it's a product. I'm going to call this my f and this my g. So f prime would be 2x, g prime would be dy dx. Another thing, by the way, if you really do want to go against the grain and be your own individual, you know, be me in 7th grade till 10th grade and get blonde streaks right here, like an anime character. I don't know why I did that. If I could go back in time, I would smack myself and say, Phil, stop it. You don't need to be an individual. But anyways, if you really want to, but you don't want to use color, you can instead write capital Y prime. I will give you full credit for that to like distinguish it from the regular Y's. That's another way to do it. I remember it just popped in my head. I remember another student doing that. So that's another way if you really don't want to write dy dx's. So anyways, f prime, 2x, g prime, the derivative of y is y prime, so dy dx. So this would be f prime g, so 2xy plus g prime, so dy dx times x squared, g prime f. And then similarly, the derivative of xy squared, this will be your f, and this will be your g. So f prime would just be 1 and G prime would be 2y dy dx. So using the product rule here, this would be f prime g, so 1 times y squared, or just y, oh, wrong color. 1y squared plus g prime, so 2y dy dx times f, which is x in this case. Now, when I rewrite it over here in the original column, I'm going to pretty it up a little bit, so I'm not going to write 1y squared, and I'm just going to make sure all the dy dx's are at the very end of each term, but it's going to be the same thing. Any questions on those two derivatives? There's nothing wrong with doing a little side work. I like maybe you're not like me, and if you can totally digest it and do it all at the same time, that's great. Perfect. I'm happy for you. Me personally, my mind starts to get a little overwhelmed in those cases. So it kind of helps me to break it down into pieces and then bring it back together. Anywho, so what we end up with then is, so the first part was, so 2xy plus x squared dy dx plus g plus the derivative of the second one, which was y squared plus 2xy dy dx equals 0. The derivative of -2 with respect to x would be 0. Yes.
For
Kevin.
EX, that goes before, but then you want to take into consideration but for EY, EX, you put that after the Y.
So that great question, Kevin. So when you're taking a derivative, when you're doing a ddx, it does need to go in front. Just like you don't write just like we don't write when we're trying to take the square root of 4, we don't write 4 square root, right? We write the square root first because that's what we're doing. We're providing that operation on the 4. But the other one, with regards to dy dx, it doesn't matter where you have it in the equation. That's just convention. Thank you for asking. That's a clarification. Dy dx, you can put it wherever you want in the multiplication. It doesn't matter to me. I just like having it at the very end, just by convention. That's what looks prettiest to me, but it's totally fine to leave it where how I wrote it in the green and blue. All right, so we have our dy dx terms and our non-dy dx terms. Let's bring, since the dy dx terms are already on the left, I'm not going to bring them to the right. I'm just going to bring my non-dy dx terms to the right. So I end up with x squared plus 2xy times dy dx. Right, those are the two terms on the left-hand side that had a dy dx. I just factored out front. That's why. So x squared dy dx, that's where I'm getting that x squared. So from this term, that's where I'm getting this. And from this term, that's where I'm getting that 2xy. And then on the right-hand side, now that's subtracted, I've got negative 2xy minus y squared. Finishing off, dy dx then, by dividing both sides by the functional or the expression right next to my dy dx, I get dy dx is equal to negative 2xy minus y squared, all divided by x squared plus 2xy. And so I hope you can kind of see the symmetry that I'm talking about here. If I were to factor out a -1 from the numerator, I get y squared plus 2xy. So it's like the same thing, but like slightly different. So pretty nifty. And please, for the love of God, do not simplify. Do not do that. No. I would write on your exam why. Why did you waste time doing this? Because it's not helpful. So this is just merely a thing I'm just kind of mentioning, just because I think it's so cool and pretty. Like when the equation is symmetric-ish, the derivative ends up being symmetric. That's almost always true. So if you're like, it's not a checking tool per se. because it doesn't guarantee the answer. But like if your original equation is symmetric-ish and your answer isn't symmetric, that would be a situation where I might go back and like double verify my answer. You know what I'm saying? So, any questions on that? This, much like the chain rule, is just something that takes practice, by the way. If you're still feeling a little bit lost on this, I promise you the more you practice it, the better. So let's go ahead and we've got that one, that one, that one, that one, that one, and that. Okay, so we've got a little bit of, so unfortunately, I think we're gonna have to keep chugging along. Okay. Sorry, I would normally give a break. I really don't want to have to keep you guys going for an hour and like 50 minutes total. You guys are superstars. You know, you need to know that doing an hour and 50 of calculus is a big ordeal. So congrats to you guys. So this one, we're gonna take the derivative of both sides. So ddx of both sides. X cosine of y plus ln of x. And on an exam, I don't need to see that step, by the way. I don't need to see it, but I do want you to write it in your notes, purely because then when you're rereading your notes when you're studying, you can look at it and say, okay, so that's what I did. I differentiated both sides of the equation. You can just go straight into it in an exam scenario, but I do like having that in your notes so that when you're looking over it, you're not like, well, what the hell happened? What happened? Well, why did this happen? So the first term on the left-hand side, that is a product of two things. That's a product of x and cosine of y. So we're going to have to do a product rule. So the derivative of that would be f prime g, so 1 cosine of y plus g prime f. G prime being cosine, or g being cosine of y. So its derivative would be negative sine of y times dy dx times x. Let me write that prettier. So negative sine of y times dy dx times x. Write that down and we'll explain it one more time. That's just the left-hand side of the equation. So f prime, the derivative of x is 1 times g, which is cosine y, plus g prime, the derivative of cosine of y would be the outer function is cosine, the inner function is y. So derivative of cosine is negative sine. That's why it's negative sine of y times the derivative of y, which is dy dx. And that's why I put it in parentheses. That's g prime times f. And then on the right-hand side, the derivative of y is dy dx. Plus 1 over x. Yes. No, absolutely not. I was going to do that. So Capri's asking, would it be wrong to write this term right here? You don't need to write this down because it's the one I'm going to do in the next step. Would it be wrong to write this as minus, like this whole thing here, as minus x sine y dy dx? Absolutely not. In fact, I would encourage you to do that once you feel comfortable. But I wanted to make sure it was very, very clear in the notes that this was g prime times f. But ideally, you get to the point where you can write that. And this is a situation, specifically for that reason, why I would bring my dy dx term to the right-hand side. Because I don't like to deal with multiple negatives. If I can avoid it. So I would bring... I was meant to use it. I would bring this over here because this is going to be subtracting a dy dx term. So I can add it to make sure that all my terms are positive. It's not required by any means. It's just, it looks prettier. So we end up with cosine, oh, wrong color. Cosine of y minus 1 over x is equal to x sine y dy dx plus dy dx. And to save on space, I'm just going to factor this underneath it. This ends up being x sine y plus 1 times dy dx. Because that's a 1 dy dx. That second term is just 1 dy dx. That's why it's x sine y plus 1. And then dividing both sides by that to get the dy dx by itself gives us our answer, which is that dy dx is equal to cosine of y minus 1 over x divided by x sine of y plus 1. Whew. And so you can see what I mean. This equation wasn't very symmetric at all. And so the answer doesn't end up being any symmetric at all. This next one, it looks a little symmetric. X squared plus y squared, and then in the inside of those parentheses, 2x squared plus 2y squared minus x. So it might be a little symmetric. We're not sure, but it probably should be a little bit. All right, I would like you guys to try this one. Try C. I will slowly fill in details. But give it a shot. Feel free to use some scratch paper. I believe in you. Believe in you. I know you guys can do it. As a total aside, while people were working on this, I don't know if you've heard about it on campus. I think they may have sent out emails about it, but just in case you did not know, apparently, Kamala Harris is going to be on campus pretty soon. I don't remember which day, but I think it's like next week. Tomorrow. Sorry, Thursday. Yeah, that's right. Thursday, tomorrow.
But in North Las Vegas.
At the North Las Vegas campus. So, and I believe the person who works in the room next to us over here, Patrick Villa, he's the faculty senate chair, and he's also a friend. He was mentioning how it's going to be 80% students, 20% faculty. So there's going to be ideally most of the space available is for students. So I mean, if you get the chance, I mean, even like regardless of your political affiliation, I mean, when's the next time you're going to be in the same city as the vice president? Pretty cool. What?
I think Kamala Harris was also in the National Guard. You see, like training.
Oh, cool.
I wasn't there with my consultant. I
Awesome.
was spectating them.
That's
And
awesome.
like their sergeant said, you better be good.
Fair. You gotta be on your best behavior. But anyways, super cool if you can get to go. Like, I'm not gonna be able to get to go. I gotta watch over my son. But if anybody gets to go, please tell me. And say Phil said hi. Go onto the stage and say Phil said hi. Just because I'd love to be in the same place as a vice president. That'd be crazy.
Oh, that's how you. Kangaroo, right?
Mm-hmm.
Gotcha.
I will explain this one, by the way, because there's some key differences that we need to be looking out on. But stick with it, guys. You got this.
Why isn't dy dx minus one?
Say what?
Why isn't the dy over dx minus one?
Oh, because the minus one is just an x. It's coming from the derivative of the minus x.
Where do you apply dy?
Whenever you take a derivative of y,
Just one.
just a y. Whenever you're taking derivatives of y's, it tacks on the dy dx.
Because of the
Because y is being thought of as a function of x. So how do we solve this? Great question, and I'm glad you asked it, Hector. It becomes okay. Guess I could write it a little bit better. I need to give more space on this problem.
what's the name? That's one example. Is that it?
There we go. Beautiful. It is beautiful.
You have to simplify that.
Absolutely. That's gonna be your task for this weekend is to bust this out with your boy or your girl, you know, and see a big bonding experience between you and your significant other. Okay, yes. Excellent question. Where did I get those things? Let's think about this. So I'm gonna go through this problem right here because this one was a size, this was a doozy.
Yeah.
But I know you can do it. You can do it. My guidance. So left-hand side, pretty nice. Derivative of x squared is 2x. Derivative of y squared, 2y dy dx. The derivative of the quantity 2x squared plus 2y squared minus x squared. So I'm going to zoom in on that aspect of it. So by the chain rule, the outer function is the second power. The inner function is 2x squared plus 2y squared minus x. So derivative of the outside, that's where this 2 gets brought up front, and it's to the first power times, notice the difference here. Notice the difference. Over here, dy dx. Here, d dx. Because I'm taking the derivative of the inside. So the only, like, the left-hand side stays 2x plus 2y dy dx for a little bit. So we're not going to deal with that. Let's just look at this section right now. So when I take the derivative of the inside, derivative of 2x squared, 4x. The derivative of 2y squared, 4y dy dx. The derivative of minus x, minus 1. Now, let's zoom back out on the full picture for just a moment and think about what our goal is. We have now, after the second line, on the third line, at this stage, we have taken the derivative. That's step 1. Step 2 is to isolate the dy dx terms. The problem here being that The dy dx term is in a trinomial, or not a trinomial, but a three-term set, a three-term expression. So what I have to do on this thing to get the dy dx term by itself, I have to distribute. I have to distribute that in so I can get the dy dx term to be able to be moved. So the reason why there's an 8x and an 8y, when I do the first term, 2 times 4x, that gives me that 8x times this. When I distribute in the second term, 2 times 4y, that's the 8y. And then the 2x squared plus 2y squared minus x times the dy dx. Then minus the 1 times this, that just gives me minus the term. Not pretty, but it's there. That's where that comes from. Now we have the dy dx terms and the non-dy dx terms. We're going to isolate them. I'd recommend, instead of having to move a bunch of things over, I just move this one. I just move this term over to the left. But it's not wrong to do it the other way around. It's not wrong. So I subtract off 8y times 2x squared plus 2y squared minus x dy dx from both sides. And then I've already factored it out. So the 2y right here, the minus 8y times 2x squared plus 2y squared minus x over here times dy dx. On the right-hand side, this stuck around. This stuck around. And then I had to subtract 2x from both sides. This is a doozy. This is a testament to your ability to write quickly. And then just divide both sides. Just divide both sides, right? A last step. Now we've isolated the dy dx terms, factored it out, and then we divide both sides to get our final answer. And that will be a disk free.
Would it be wrong if we to like the first part and making it 4x squared plus 4y squared minus 2 and then divide that from the other side and then minus 2y dy dx and put it on the other side?
I see. So the thing is, Capri brings up an excellent point. This was the way my mind originally thought of doing this. But you can do any algebra that you want to get to the end product. So another option, I'm going to show you another way to have done this. At this stage, copy. So I'm going to do this just as a side, just to show you something. What you could have done, totally legitimate to do so, would be, if you wanted to, you could divide both sides of the equation by the 2 times 2x squared plus 2y squared minus x to both sides. And then you get x over 2x squared plus 2y squared minus x plus y over 2x squared plus 2y squared minus x times dy dx is equal to 4x plus 4y dy dx minus 1. You could do that. And maybe that's more approachable to you. Like you didn't want to deal with that thing, like that really long term that you had to multiply into all 3 terms. Now it's only applied to 2 terms. The reason why it's x and y and not 2x and 2y is that I canceled when I divided it into both things. When I took this and divided it into 2x, the 2's canceled. When I took it and divided into the 2y dyx, the 2's canceled. This might have been more approachable to you. Now, all I need to do is bring these two, for the people watching the recording, now all I need to do is take this term and this term, combine them and bring this term to the right, whatever we want to do, and you get the same answer. It would look really different, but it's the same thing. As long as the algebra is valid, I do not care. So if you liked this way better, awesome. Another option would have been to, like, another way you could have done it is you could have rewritten this you could have rewritten this thing right here as 4x minus 1 plus 4y dy dx. That way you only have to distribute it into two things. That's another way. Do you have to do that? No, but I'm showing you so you can think about it in multiple different ways. It's a very, very useful skill is to like, instead of distributing into all three things or whatever, you can group two things or group four things, whatever you want to do. But any of those things is valid. So, doozy of a problem, but a good one. I think we're stronger mathematicians for it. I think we've learned a little bit. We've grown as human beings. A little more rugged. We're like my facial hair right now. We're just a little bit. We're a little bit scratchy. Driving me crazy. I need a shave. So, any other questions on that one? I should have given you more space for that problem. That problem was a little long. But all right. And one of the last notes on the first page of like the procedure problem was saying that we can do all the things we know and love, right? We can find tangent lines, we can find second derivatives and all that jazz, right? So you can find the equation of the line tangent to the curve tangent of x plus y minus 1 is equal to xy plus 3x at the point 0, 1. The good news with implicit differentiation tangent lines is that they almost always give you the point. So there's no need to plug in the original function to find the coordinate point. So that's the good news. So finding an equation of tangent line. If you haven't seen it, if you haven't seen this question before, we approach it with open arms. Just like when like this looks like a big temper tantrum of a problem. But with your child, you do not just say, I hate you, go away from me. You approach it with open arms. We say, how do we fix this problem? How do we approach it? What do I need to do? Tangent line. As soon as I hear tangent line, my mind is saying, I need to find the slope. I need a slope and I need a point. Already got the point, just need the slope. How do I find slope? You see this kind of deduction that I'm doing in my head. I don't have this process memorized. I just ask myself these questions and let my mind fill in the blanks. That is the best way to get your mind to be top tier mathematically. Okay, so I need to find the slope. The slope is given by the derivative. I need to take the derivative of that. So let's differentiate that thing. So for slope, d dx on both sides. So d dx of tangent of x plus y minus 1 equals the derivative, so d dx of xy plus 3x. I'm going to slowly fill in the details. I'd like you to do the same. Try and do it yourself. Our function on the left-hand side is tangent. So we should get secant squared of x plus y minus 1 times the derivative. So 1 plus dy dx equals, that's the left-hand side. Derivative of the outside, derivative of tangent, secant squared of x plus y minus 1, derivative of the inside, derivative of x is 1, the derivative of y is dy dx, and the derivative of minus 1 is 0. On the right-hand side, that's going to be a product rule for that first term, f prime g plus g prime f. So that's going to be 1y plus dy dx times x plus 3. You have a question? A question? It's okay if you just want to talk to like it's, but it might be a good question. Oh, it's the derivative, like they're each separate, like they're added by a plus. So the derivative of x is just 1, the derivative of y is just dy dx. Since they're separated by, like if it was a multiplication or whatever, that might be different. Maybe that's not answering your question, but. Now here's a cool thing. So we can solve for dy dx here if we want to. Absolutely. But the question is not asking us to find dy dx. It's asking us, technically speaking, to find dy dx evaluated at 0, 1. So if we don't want to solve for dy dx like this, we could just plug in 0 and 1 and simplify everything. So instead of having functions, we now just have numbers. Does that make sense what I'm saying? Let me say that one more time. So I could right now just plug in x equals 0 and y equals 1, and then let those things all become numbers. Because I'm not being asked to find dy dx for any x and y. I'm just being asked to find dy dx for 0, 1. Now so that's one way to do it. But just so we get more practice isolating it, what I'm going to do is I'm going to distribute in that y term. So we get secant squared of x plus y minus 1 plus secant squared x plus y minus 1 dy dx equals y plus x dy dx plus 3. I will show you the difference over here. We'll do both of them. I think it's more important than trying to hastily get through this. So we get secant squared of x plus y minus 1 minus x dy dx is equal to y plus 3 minus secant squared of x plus y minus 1. Take a second to digest that and write it down because I wrote it so dang quickly. Family writing that too fast. I'm sorry. Sorry, I should slow down. Thank you, whichever student said that. Take a second. Once you've written it down, digest it. This is a piece of sourdough bread. It's very chewy. Take a second to bite down pretty hard until it tastes delicious. Or a piece of stale bread that we have to let our saliva kind of break it down first for a second. So just as a reminder, so I subtracted the x dy dx to the left-hand side, subtracted the secant squared x plus y minus 1 to get it on the right-hand side. And then I immediately factored it out. I saved on an extra space here. So I brought this term over and then I factored out the dy dx. That's why it's secant squared x plus y minus 1 on right here, and then an x, and then the dy dx on the outside. Here, the y and the 3 stick around, and then I subtracted off this to bring it on the other side. That gives me at the end of the day, dy dx is equal to y plus 3 minus secant squared of x plus y minus 1 divided by secant squared x plus y minus 1 minus x. Now I can plug in 0 and 1 for x and y. So dy dx at 0, 1. So that vertical line being evaluated at the quantity 0, 1. So at x equals 0 and y equals 1. That gives me 1 plus 3 minus secant squared of 0 plus 1 minus 1. So secant squared of 0 divided by secant squared of 0 minus 0. And what's secant squared of 0? 1. Exactly right. Because secant is 1 over cosine. Cosine of 0 is 1. So secant of 0 is 1. Secant of 0 is 1 over 1, which means the secant squared of 0 is 1 squared. 1. So we end up with 1 plus 3 minus 1 over 1, which is 3. That is our MTAN. And our point was already given. 0, comma 1. So y minus 1 is equal to m 3x minus 0 by the point slope formula, or y equals 3x plus 1. Either way is fine with me. So you know which one I'm more partial to. That is our answer. Now I want to show you the faster way that is only niche to this situation, what I was talking about earlier. You don't have to solve for dy dx because we're not being asked to find dy dx. So an alternative, so once we have this alternative, plug in x equals 0 and y equals 1 now. So that we don't have to go through that algebra of getting the dy dx by itself. We're only being asked to find dy dx at 0, comma 1, so might as well just plug it in now and deal with nicer numbers instead of having to write secant squared x plus y minus 1 every damn time. So plugging in 0 into this equation here, you'd get secant squared of 0 plus secant squared of 0 dy dx equals 1 plus 0 plus 3. So make sure you understand that, write that down and then digest it. Plugging in 0 and 1. So 0 plus 1 minus 1, that's 0. That's why it's secant squared of 0. Same thing for the next term, but then there's a dy dx on it. 1 for y, that's why I get a 1. 0 times dy dx, that goes away. That's why it's just 0. And then 3 sticks around. The reason why this is 0 is because it's going to be 0 times dy dx, which is just going to be 0. At the end of the day, that will be 1 plus dy dx equals 1 plus 0 plus 3 equals 4. Dy dx evaluated at 0, 1 equals 3. Much faster. But we have to understand what we're doing. So, yes.
Could you also plug it into the equation right before it?
Yes, absolutely. Great question. Great question. You could absolutely plug it into the earlier equation as well. You could have. I got a little bit. You could have just done it here too. In fact, it would have been easier to do it here instead. Good catch. Good catch. All right. Whew. Okay. Let's keep going. All right, now we can find second derivatives, third derivatives with implicit differentiation. Are you ready?
No.
Are you ready to have some fun and some algebra? Lots and lots of algebra. So much. If this was 2008, I would say all the algebra, right? For any of those millennials out there. Is anybody here a millennial? No, I don't think so. Okay, wow. Okay, so find d squared y over dx squared. That's meaning find the second derivative. If I need to find the second derivative, I need to find at least the first derivative. So find first deriv first. So d dx on both sides. Dx of x squared y squared minus 2x and 3. A little behind, but that's okay. It's okay. I can skip over 2.6 briefly. All right. So by the product rule, the left-hand side becomes 2xy squared plus 2y squared dy dx times x squared. Oh, no, not 2y squared, 2y, excuse me. F prime g plus g prime f. There's no chain rule. Well, like, there is a chain rule with the y squared, but there's no chain rule because there's no, there's no inside and outside function. It's two functions being multiplied together.
Inside the parentheses.
Yes. There's no chain rule going on here per se. There is a chain rule with the y squared, but that's a minor one. -2 is equal to 0. Let's solve for dy dx. All right, so we get 2y dy dx. 2x squared y. 2x squared y dy dx. Let me write that just better. 2x squared y dy dx is equal to 2 plus 2xy squared. So that means that dy dx is equal to 2 plus 2xy squared divided by 2x squared y. Yes.
Remove 2x twice.
It should be minus. It should be minus. It should be minus. Thank you. That should be a minus sign there. The right-hand side should be 2 minus 2xy squared. So 2 minus 2xy squared. Thank you for catching that. All right. That's first derivative. How would I find the second derivative? Just do it again. Differentiate both sides of this equation. Now find second derivative by dy dx ing both sides again. So we're going to find the second derivative by taking the derivative of both sides again. I'm going to write it in blue this time just for funsies. D dx of the right-hand side equals d dx of the left, d dx of the left-hand side equals d dx of the right-hand side. So d dx of dy dx equals d dx of 2 minus 2xy squared, all divided by 2x squared y. And yes, this is going to be a nightmare, but it's going to be a good nightmare.
But something like that.
I just say things sometimes that doesn't make any sense. I think it's a good nightmare. But every once in a while, I have no filter. So on the left-hand side, we get d squared y dx squared. We get the second derivative. Beautiful. On the numerator, 2 d's and a y, that's why it's d squared y, and then there's 2 dx's, that's why it's dx squared. Or the second derivative. Because we're taking the derivative of dy dx, taking the derivative of y prime gives us y double prime. Now, we had to take the derivative of the numerator and the denominator. It's a quotient rule, right? So this is our f, which implies that f prime be 0 minus how do I want to write this?
Isn't it F prime times 2 plus 2?
Yes, so we're gonna have to do a product rule within this quotient rule.
I would say F equals that, but F prime.
So 0 and then plus f prime, so negative 2y squared plus g prime 2y dy dx times negative 2x. The derivative of 2 is 0. The derivative of negative 2xy squared would be negative 2y squared plus 2y dy dx times negative 2x. Writing that a little prettier, that would be negative 2y squared minus 4xy dy dx. Okay. Question is, what's dy dx? Oh, wait a minute. What's dy dx? We found it right there. So, my friends, f prime is negative 2y squared minus 4xy times 2 minus 2xy squared over 2x squared y. As my son would say, very, very hilarious. That is f prime. The good news with the second derivatives and the third derivatives and so on and so forth is the left-hand side is always the second, third derivative. There's no solving again. Left-hand side always stays the derivative. So bad news bears is that now we have to just rewrite dy dx in there. That's f prime. Ah! And that's g. So g prime would be 4xy plus 2x squared dy dx. And we're already out of time. I'm sorry to keep you guys a little bit late. You guys are champs. We're gonna finish this one and then cry. We're gonna have a good cry together, and then we're gonna be okay. So that's gonna be 4xy plus 2x squared. There's 2 minus 2xy squared over 2x squared y. Who Nelly? Who Nelly? I'm sorry to keep you late. If you need to get going, I understand. I'm trying to finish this up just really quickly. So once again, taking the derivative of the right-hand side, that's a quotient rule. So we need to identify the top function f and the bottom function g, so we can do the f prime g minus g prime f. When we take the derivative of f by a product rule that's in there, we get 2 negative 2y squared plus or minus 4xy dy dx. But dy dx we found up above to be 2 minus 2xy squared over 2x squared y. So that's what we have. So at the end of the day, f prime, so negative 2y squared minus 4xy times 2 minus 2x squared, 2xy squared over 2x squared y. That's f prime times g, 2x squared y, minus g prime, 4xy plus 2x squared times 2 minus 2x y squared over 2x squared y times g. So I don't have enough room, so I'm going to have to bust this down. Make this smaller. Times g, so times f, which is 2 minus 2xy squared, all divided by 2x squared y squared. And that is your answer. So sorry to keep you guys late. I promise I don't do that very often. I won't do that. I'll try to make sure that never happens again. But that is what we've got. We will recap that on Monday a little bit, and then move on to the rest of 2.5, which is one more thing, and then 2.6 and or 2.7. The good news is 2.8. I think we have 2 days for 2.7. So
no quiz on Monday.
no quiz on Monday. This was the only week that had 2 quizzes. All right, guys? Yes.
Next week on Wednesday.
Yes, the exam redo. No, there's no exam on the next Wednesday. It's 2 Wednesdays from now. Not next Wednesday, but the Wednesday after is our next exam. So if you guys have any questions, feel free to email me. Please start working on that exam redo to get it done and out of the way so you don't have to worry about it too much. If you have any questions, email me. Otherwise, I will see you guys on Monday. Have a great weekend.